Hello, welcome to Multivariable Calculus Lecture 1. So in this lecture, we're going to be mainly talking about functions in 3D and partial differentiation. So we're all used to seeing functions in 2 dimensions, where we have 2 spatial axes, our x and our y axes, and we have some curve, and let's call this curve f. And we are used to seeing the properties of this curve by finding the slope of this curve, by finding the area under this curve, and we can all do this with simple single variable calculus. But what happens if we add another spatial axis? So now, instead of having 2 dimensions, now we've increased our dimensionality to 3, and so now here we have, instead of 2 axes, we have 3 axes, the x, y, and the z axis. And so in 2 dimensions, y acts as the output and x acts as the input, right? But in 3 dimensions, now we have z as the output, and x and y are inputs. And so in two dimensions, we have some function of x, where x is our input and f of x or y is our output. Whereas in 3 dimensions, now we have both x and y as inputs, and so our function is x and y. And so x and y, we plug both x and y into our function, and we spit out a z value. So why do we use these kind of functions? Well, everyday objects like this rock, or this brick here, can be described or approximated using 3-dimensional functions. And 2-dimensional functions don't really have that property to describe space. And so that's one of the main reasons that we use 3 dimensions, and we can see a lot of properties about our 3-dimensional functions. And so one of the main differences between 2 dimensions and 3 dimensions is, of course, the amount of space and the dimensionality of each of them. And so in 2 dimensions here, this is what our xy plane would look like. And in 3 dimensions, this is what our space would look like. And notice how I'm using the words plane and space, because these are very, very common terms that are used to describe both 2D and 3D. Here's x, y, and z. And so these terms will be very, very relevant in future lectures, as I'm going to be referring to different kinds of theorems and different properties using the words plane and space. So what are some functions that we can look at in 3 dimensions? For example, we've all seen what a circle looks like, and we can add another dimension, and now we basically have a sphere. And so a sphere looks like this. It's got some inner radius, and there are countless others that we can countless other shapes that we can describe. So we have spheres, we can have paraboloids. So a paraboloid here is essentially what we would think of as a parabola, yet we've added another dimension. And so now our paraboloid looks like this. Our paraboloid looks like almost like a bowl instead of just 2 dimensions. And we have many other functions. We can say we have hyperboloids, we have planes, we have ellipsoids. And so how can we use functions to describe these specific types of shapes? So we're all used to the parabola being the equation we have. Let's call this our unit parabola. We have y equal x squared. This is our unit parabola. Now, if we wanted to describe the paraboloid, our paraboloid now is z is equal to x squared plus y squared. And so this is kind of the general pattern. And so if we looked at more functions, we could see what happens if we increase the dimension. So for example, a circle our general equation would be x squared plus y squared is r squared, and that makes our circle. For a sphere, our general equation would now be x squared plus y squared plus z squared is r squared. And so this is kind of the pattern of how we are increasing the dimensions of the functions to add another variable. And so I'm going to provide one more example. I'm going to provide the example of a line versus a plane. So here we have a line, and I'm going to give a very, very general formula for a line. For a line in 2 dimensions, our formula is y is some constant times x plus some constant. For a plane, if we were to translate that and we were to follow the same pattern as we've done here, now what we've essentially done is we're going to add another variable. So now for a plane 3D, our equation is now z is equal to constant 1 times x plus constant 1 times y plus constant 3. Alright, so this is the general formula for our plane. And so this is going to be especially relevant later on in the video when I talk about tangent planes. So let's look at some of the properties of 3-dimensional functions. So for functions in 3 dimensions, and again I'm going to use one of these examples on the side. That's one of these rocks. I will use this one right here. Let's call this one a function in 3 dimensions. And let's take a look at its properties. Actually, I'm going to choose a different one here. Right here. And let's take a look at this rock's properties. And let's say that this rock can be approximated using some function in 3 dimensions. So if we take a look at the slope of this specific rock right here, we can see that if we point our direction of view along this way, the slope barely changes. Yet if we point our direction of view this way, our slope is increasing and decreasing fairly rapidly. And so for all 3-dimensional functions, the slope may vary depending on the point of view or direction we're looking at it, even if it's at the exact same point. So I'm going to give an example. I'm going to give the example of a paraboloid. So we have z is x squared plus y squared. And I'm going to draw out my paraboloid here. And let's choose a point. I'm going to make this easy. I'm going to choose the point 1, 1, 2, just because they're very small numbers. And I'm going to say, okay, here's my x, here's my y, so I move along 1, 1, and then 2. And let's say this is the point right here. This is my point. And so if we were to look at this, if we looked at this point this way, the slope may be changing not much at all, but if we look at it this way, the slope could be changing a huge amount. So that is very, very important because in 2 dimensions, there's only one slope. There's the slope of the line at a given point, but in 3 dimensions, it becomes a little more complicated. And so now we have to analyze it at different points of view to find the slope. And so I'm going to introduce what's called the partial derivative. Okay, so we're all used to the ordinary derivative, and all it does is it finds the slope. And I'll draw a little diagram here. We have a curve, and let's say this is our slope, this is at the point, and that's our tangent line. And there is one given slope, but since at a given point in 3 dimensions there can be more than one or infinitely many given slopes, then we have to essentially lock our view into one direction to see what the slope is in that single direction. And so for the partial derivatives, we restrict ourselves to only the x and y directions instead of looking at all directions because it makes it a lot easier. So for example, I'm going to draw this again. Here's my x, y, and z axes. And let's say I had some curve. Who knows what this curve looked like? Okay. And let's say I wanted to take a slice of this curve parallel to the x-axis at some y. And so this is what my slice looks like. And so let's say I were to zoom in on the slice, and this is all theoretical. Let's say I were to zoom in on the slice, and this slice here that I've taken of this curve, whatever this curve may look like in three-dimensional space, now looks like this, right? But now I can find the slope. Now that I've basically taken a slice of my function and set y to be a constant here, right? X varies, and so here I'm going to draw a diagram. This is my x-axis, this is my z-axis. And so now I've basically taken a slice of my function at a given y, and now I can evaluate the slope at the point in the direction of the x-axis. And so that's called the partial derivative, and that's called the partial derivative with respect to x. And so we can do the exact same thing. We can, let's say I'm going to not look at it in this direction, but I'm going to look at it, let's say at a given x value that remains constant. And I go this way, and I take a slice this way. Now maybe the function may look like this. Who knows? Maybe it's not going to look like that, but who knows? It could look like anything. And now we can find the same thing. Now we can find the slope in the direction of the y-axis. And so this is what's called the partial derivative. Is essentially what we're doing is we're taking slices of our function at a given x or y value, and we are evaluating the slope in the direction of the x and y axes. And so let's say for my function I wanted to find the partial derivative with respect to x. Well, what does that even look like? What's the notation, right? So let's say I have some function. Z is f of x, y. This is very, very general. I'm just stating that z is my output. And let's say I said that z, or f of x, y, was x squared plus y squared. So this is the paraboloid example that I used in previously. So what would this look like? So the partial derivative with respect to x, and this is how we write it. Instead of saying df dx, we would say del f del x. The partial derivative with respect to x, what we did is when we looked at our function, and I'll actually draw the function this time. What we did is, here's the x-axis, here's the y-axis. We are essentially slicing it in the x direction. And now this could be parallel to the x-axis, or it could be on the x-axis, we never know. So I'm going to choose some random value of y to slice, and we've basically taken a slice this way of our paraboloid. Okay, and so what happens when, how do we find something like this? Well, essentially what we're doing is when we're taking the partial derivative with respect to x, or with respect to any variable, we're essentially going to take all the other variables that we see and treat them like constants, right? So here, y, it is a constant. That's what we're doing, is we're essentially taking a slice, and y remains constant the whole time in that slice. And if you differentiate a constant, it goes to 0. And so what our partial derivative with respect to x would look like would be here, where you set ordinary derivative is 2x, and when we differentiate a constant squared, it's just 0. So this is our partial derivative with respect to x. And so if we actually took a look at what this looked like, for example, let's say at y equals 0, right? Our curve would look exactly like a paraboloid. If we set y to be 0, now our function is just, this is z, this is x, a parabola, right? And the derivative of a parabola is just 2x. That's all it is. We know that from single variable calculus. So we can expect that. And the same thing with the partial derivative with respect to y. The partial derivative with respect to y would be, and now what we've done is, instead of doing this here, now we've treated x as a constant, and we're slicing along some constant x parallel or at the y-axis. We're taking a slice. This is not parallel, but we're taking a slice here. And now it's just going to look like this. It's going to look like the same thing. It's at 0 or whatever constant. It's just going to look like a parabola. And if we have y and z, now essentially it's just 2y. It's the same thing. We're treated x like a constant squared is 0, and 2y. That's all it is. And so that's the idea of the partial derivative, is we're taking a slice of this function and we're treating other variables as a constant, and we're basically differentiating those variables that we're interested in this case y or x. So partial derivative with respect to x means in the x direction or in the y direction. Okay. So I'm going to give a quick example. So if I had, let's say, the function, if I had the function, and I'll say this is x squared cosine y. This is my function. I don't know what this function looks like, but this is what my function is. If I wanted to find the partial derivative with respect to x, this is a constant, because the cosine of a constant is a constant. And it would just be a constant times our, so it would, and if we can rewrite this, right? We can rewrite this and say, okay, at some constant y, f of xy is equal to constant 1 times x squared. So this is this makes it easier to read because sometimes the x and the y can confuse us. So now if we differentiate a constant times the variable or whatever that we're looking at, now we just keep this constant stays the same. And so our our partial derivative with respect to x would just be 2 times constant 1 x. Well, in this case, constant 1 is just cosine y, so it would just be 2x cosine y. And because we don't know what our y is, it's just an arbitrary y, so it would just be cosine y. Okay, and if we looked at, let's say, partial derivative with respect to y, now this x squared is a constant, and now what we're looking for is cosine y. So now at some constant x, right? Let's just write it out as constant 1 times cosine of y. And we've wanted to find the derivative with respect to y. Now it's just negative constant 1 sine y. And so, but constant 1 is just x squared because we don't know what x value is. So it would just be negative x squared sine y. Okay, that's a worked example of the partial derivative. I hope the intuition and I hope kind of the visualization made sense. So I'm going to move on to something very, very related, but also something fairly different. Okay. Actually, no. This is very, very related. So we've looked at what this looks like, but now I'm going to write out the formal definition for the partial derivative. So we're used to the formal definition for our ordinary derivative. I'll just write that out. This is 2d limit as h goes to 0. H is our change in x. Or we can call it h, we can call it change in x. I'm just going to keep it as at h of f of x plus h minus f of x over h. That's our ordinary derivative that we're very, very used to. This is in h. Now, for partial derivatives, we can do something very, very similar. So now, let's say I had some function, f of x, y, and I'm going to assume it's differentiable, just for the simplicity of this lecture. And let's say I wanted to find the partial derivative with respect to x. Okay. So again, what we're going to do, I'm going to call it change in x, and instead of, I'll say h is change in x or change in y. But it's very, very similar. H is just simply change in x in 2D, and I'm going to also include change in y. But with respect to x, what we did, as shown in the previous few minutes, we essentially took small steps in the x direction and set y to be constant. So y, in this case, doesn't even matter because y is not changing at all. So it would be f of x plus change in x, comma, y minus f of x comma y over change in x. Oh, and hold on. And this would just be limit as delta x goes to 0. And delta x in this case is just h, but I'm writing it as delta x to make it more clear because we have delta x and delta y in the future. So here what this is saying is we have, it's the same thing as finding the slope between 2 points, except now we're shrinking this delta x infinitely small to find our exact partial derivative. Okay, and so here's my change in x, right? Here's my change in f over change in x, and that's essentially what I'm writing here. Now, if I wanted to write partial f, partial y, it'd be very, very similar, except now y is changing infinitely small. And so we have function x comma y plus delta y minus f of x comma y over delta y. And that's our partial derivative with respect to y. Okay. So here's what this is the formal definition. So I'm gonna write this down. This is formal definition. And so that you can see this is very, very similar to the partial. It is this ordinary derivative, except now we're just isolating to a single variable, x or y. And in this video and the next few videos, I'll be talking about mainly Cartesian coordinates because it can get a little more complicated with different types of coordinates. Okay. So we've looked at lots of first order partial derivatives, but now we can look at higher order partial derivatives. So we can, so let's say we have a function x and y again, and we have a defined partial derivative with respect to x, partial derivative with respect to y, and we're going to assume that f of xy is at least twice differentiable or even more, who knows. And so there are such things as higher order partial derivatives, just like there are higher order ordinary derivatives, right? Ordinary derivatives, we have d squared or d to the n x, or dy over dx to the n, right? This is our nth order derivative. We can do the exact same thing with partial derivatives, except we can make it more interesting and make it different by, instead of just doing this with one variable, we can do it with multiple variables, we can do it with a single variable, we can do it any combination. So if we take a look at this function here, we don't know what this function is, it could be anything. And I'll use the same example as last time, 2x cosine y. This is just because it's an easy function to differentiate. So if we take a look at, x squared cosine y. Okay, x squared cosine y, this is our function. And we said, okay, I want to find del f del x, right? Based on our previous rules, it would just be 2x cosine y. Del f del y, based on what I said previously, it would just be negative x squared sine y, right? So that's cool. Now what if we do this again? What if we say, I want to find now del squared f del y squared. So we basically are differentiating this thing again with respect to y. So now it would be again negative x squared cosine y. Or if we wanted to find del squared f del x squared, it would just be here 2 cosine y. Okay, so this doesn't really get us anywhere. All we're doing is essentially we're finding the concavity now. Instead of the slope, we're finding the concavity in our y or x directions, but we can change it up. We can actually say, I want to differentiate with respect to x, and then I want to differentiate with respect to y, or I want to differentiate with respect to y, then x, either one. And so if we look at, what does that even look like, right? This is, the notation would be, again, it's a second partial derivative, but now we want to differentiate with respect to x, then differentiate with respect to y. So that's what it would look like. That's the notation. And so if we took this, we know that this is our del f del y, right? And so this is equal to del y of del f del x. that's essentially what we're doing, is I know this is kind of confusing with how these two are switched, but when we read this, we read it like left or right to left, and so we're doing whatever's in our parentheses first, and then we're applying this. So when we read it this way, we're doing this first, then this first. And so here's del f del x. We've already established what that is, right? If we differentiate with this with respect to y, now we get negative 2x sine y. Okay? So that's what this is. This is the same thing as this. Now what if we switch it up? What if we say del squared f over del y del x? Well, that's the same thing as saying del x of del f del y, right? We know what del f del y is. Del f del y is this. That's what that is. If we differentiate this with respect to x, now we cover this up, this is a constant, we get negative 2x sine y. So this here, negative 2x sine y. And if you actually notice that these are the same thing. These are exactly the same thing. And so this is, oh.
Cut the recording, there are only 10 seconds left. 3.
Okay, and so now you can see that these two are actually exactly the same. So essentially what we've done is we've taken a partial derivative with respect to x, then y, or with respect to y, then x, and we've achieved the same result. And this is actually not a coincidence, this is a real scenario, and this is called the symmetry of the second partial derivatives. And so I'm going to write this out just to make it clear. So here, this is the phenomenon called the symmetry of second partial derivatives. Okay, so what this is saying is, if we have a function f and we differentiate it with respect to y, or x then y, it achieves the same result as with respect to y then x. And this applies. This is very, very important because it shows kind of these balances and these connections between our partial derivatives. And if we actually visualize this, we can see it makes sense because we're essentially isolating a point and we're finding the concavity in the x and y, and it's the same thing if we do both. And so if we were to and here another way of actually writing our partial derivatives, which makes it way easier. Let's say that u is some function x and y. Let's make it u. One way of writing this right here is saying u sub x y, indicating that we're differentiating with respect to x, then with respect to y. Or one way of writing this here is saying u sub y x. And so essentially, if we have some function u, here's u, we can say, okay, I want to differentiate with respect to x, so u sub x, u sub y, right? Those are our two partial derivatives. Let's say I want to do this again, u sub x, x, or u sub y, y. But we can also do this, u sub x, y, or u sub y, x, and these two are exactly the same. And this is what's very, very important. This is a very, very interesting phenomenon in second partial derivatives. Okay. So that's pretty cool. That's kind of a neat little concept. So how do we apply partial derivatives to real world scenarios and kind of problems that we're faced with in math? So I'm gonna do this quite a lot in these lectures, is I'm gonna actually I'm going to kind of relate things back to 2 dimensions, because a very, very important strategy of simplifying problems in 3 dimensions is relating them or even reducing them just to 2 dimensions. So in 2 dimensions, right, we're very used to, let's say this is a curve, a tangent line at some point, and let's call this point x naught, y naught, okay? And the slope of the tangent line is the slope of our point. Okay. That's very, very important. If we were to expand this to space, not just the plane, we would get something that's not a line, but an infinite sum of lines that depending on the orientation or the direction you look at it, shows the slope of the point, at any orientation. So an infinite sum of lines essentially would create a plane. And so instead of, in 2D we have 2D, we have tangent line. And in 3D, we have a tangent plane. So again, I'm going to use a lot of these little rock samples. I'm going to use this one this time. Okay, so here I have some rock here, and we can still have a tangent line. We can still have some line, like I'll say my finger is the line here. That's tangent. But now what we can have is what gives us a lot more information is a plane that's tangent to some point. And so our plane now, if we were to look at this plane in the x direction, it would give us our slope in the x direction, or the same thing with the y. So tangent planes. Okay. This is the second to last portion of this lecture. And I will actually provide an example problem with tangent planes. So I'm going to write this down here. This is a very, very important concept. Okay, tangent planes. So with tangent planes, I don't really know how to draw a tangent plane, but I hope it's easy to visualize. So as I mentioned earlier, right, our equation of a line, because our line, if we bump it up a dimension kind of, and we add another variable, would translate to a plane. So the equation for a plane here, this is just a very, very general plane. It can describe any plane. It can describe the xy plane. It can describe a curve, like a bent, or an angled plane. It can describe anything. So it'd be z is some constant times x plus some constant times y plus some constant. Okay. And just like the properties with the tangent line, where the slope of the tangent line represents the slope of our point, the slope of our tangent plane in the x direction represents our slope of the point in the x direction, or the slope of our tangent plane in the y direction represents our slope of the function in the y direction at any given point. So let's use a very, very interesting example. Let's use a function. Okay. Let's say we have a function of x and y is x cubed y squared minus x over y. Okay, this is kind of a weird function, but I guess it just shows that we can have all sorts of functions in 3 dimensions. Let's say 0.22, those are our inputs. We get 8, 4, 32 minus 1. Okay, 33. That's our z value, or our output value, or whatever you want to call it. So that's our point, and we want to analyze what goes on at this point. Okay, and we'll analyze what goes on, and then we'll eventually find the equation of the tangent plane at this given point here. Okay, so if we find the derivative with respect to x, this is based on the previous rules. We get 3x squared y squared minus 1 over y. Yep, okay. That's our derivative with respect to x, our partial derivative, and our partial derivative with respect to y is 2yx cubed plus x over y squared. Okay. This one I just used the rule, the d dx of x to the n is just nx, or x to the n minus 1. That's just what I did here, except now I have a negative value for n. Okay, okay, so that's what our partial derivatives look like. If we want to evaluate the slope in our y direction or x direction, we simply just plug in the points. And we're not going to really use 33 here for the first part, because we're simply just plugging in the input points. If we plug in 2, we end up getting, what is that? 12 times 4, 48 minus 1/2. So at the point here, at point, and I'll call it P. this is point P just to make it easy. It should be, hold on, 47.5. Yeah. Okay. It should be 47.5. 16. Yep. Okay. And here, if we evaluate this at point P, we get 4, 8, 32. It's 1/2. We get 32.5. So that's our here, and that's at point P. Okay. So this is what we get at some specific point P. So this is our slope in the y direction, our slope in the x direction. These are really, really high slopes. Yeah. Okay. So I'm gonna erase this part here, and I'm gonna erase. Okay, and I'm gonna keep these values. I'm gonna just trust that we kind of remember the function, and I'll rewrite everything here. Okay. Okay, so we essentially have here our function x and y is x cubed y squared minus x over y, and I'm going to say partial f partial x evaluated at point P is equal to 47.5. Partial f partial y evaluated at point P is equal to 32.5, and this is our point P is 2, 2, 33. Okay. So, okay, I'm gonna erase this, I'm gonna erase this. Okay. This is our slopes here, and if we recall, this is our equation for the tangent plane. So constant 1x plus constant 3. Okay, and our tangent plane, this is a property of a tangent plane, but also properties of tangent lines. In the x direction here, if we look in the x direction, our slope of the tangent plane in the x direction should equal the slope of our function in the x direction. So if we actually differentiate this tangent plane here to find the slope in the x direction, dz, or del z, del x, these are all constants, right? Y is treated as a constant, constant is just constant. And so now we're left with just constant 1. That's our slope. And we know, and also the tangent plane has the same point as our function. And so we know at this point here, constant 1 must equal 47.5, because that's the slope in the x direction is constant 1. You can see the same thing with constant 2. It's just 32.5. And so now we're left with constant 3. Now we're left with kind of the struggle of figuring out constant 3. So constant 3, essentially what it does is it just shifts the tangent plane up or down and ensures that our plane is truly tangent to our point, and it only hits the graph at that singular point, and it doesn't, and it reflects the slope at that point. So we already know this already reflects the slope, but here is what makes it tangent. Here, the constant 3 is what makes it truly able to only hit it at one spot, because now we've essentially just shifted up or down. Okay. So constant 3, all we have to do is in constant 3 is we have to plug in our point 2233 and figure out, and 2233, and we just solve for constant 3. So in this case it would be, so 33 is z, so 33 is equal to constant 1 times x. Well, constant 1 we've established is 47.5 times 2, and then plus constant 2, which is 32.5 times 2, and now just constant 3. Okay, so our constant 3 value is 127. I don't actually have a calculator on me right now, so but this, if you just calculate this out, it ends up being 127. So our final equation for the tangent line here is z is 47.5x plus 32.5y minus 127. This is our official equation for the tangent line. It's kind of a messy equation, but that's the equation. Okay, and so we can find the tangent plane. It's kind of useful to know with the tangent plane what the slope is, and it's a very, very easy way to show the slope of our function. Okay. So this is the last topic of the day, and it relates to kind of the ordinary derivative as well as the partial derivative. So we've all seen this infinitesimal d, right? Whether it be dy or dx or dz, who knows? It could be anything. d theta, dr. It could be d phi. I'll just include that one because that'll be relevant later on. Okay, we got all these weird infinitesimals, right? And then all of a sudden, we are introduced to del x or del y or del whatnot, right? And it keeps going. We can have anything. We can have du, del u, anything. And so this is really, really important because essentially what they do is essentially they sort of mean the same thing, except this is more applied to the case in 2 dimensions, whereas this is, or I'm sorry, not 2 dimensions. So this right here is kind of, if you just isolate your view to a single variable, this is kind of what you'd be using here or whatnot, right? Now, with the partials, or partial infinitesimals, now we are saying, okay, we're taking a small step in some certain direction, some x direction, y direction, z direction. Okay, so how do we relate the two? We can actually, there's a really, really interesting and important concept that actually relates the idea of ordinary, whether d times or d variable and del of some variable. Okay, and it's called the total differential. Okay, so we're very used to seeing our derivative. We can write it as limit as delta t goes to 0 of change in f of change in t. This is the df dt. This is very, very important to understand that this is essentially what we're saying is as delta goes to 0, we now turn our deltas into d's, and d is an infinitely small change, whereas delta ranges from any change. So how do we actually find something like df, for example? Let's say I want to find df. So I know that I'm going to write this out here. So I know that if we said, okay, I want to find the change in the x direction or y direction, we restrict our view to just x and y. But if we're saying I want to find the change in f, now essentially what we've done is, okay, I want to find the change in both x and y combined to form our f. So change in f, so change in f here is equal to f, and this is for some function x, f of x, y. F of x plus delta x, comma y plus delta y minus f of x, y. And over 1. That's just what it is. That's my change in f, right? All right, we have some function that we both added a small amount of x, small amount of y, and then we're subtracting it by our initial amount, and now we're getting what of our change in our y value is. That's just what we've done. And it's the same thing with saying change in y is just f, is just some small change in x, but now we're saying small change in x and small change in y. Okay, so I'm going to write this here. This is actually kind of important to know. If we said delta y for a function of x equal y, delta y is just f of x plus delta x minus f of x. That's all we've done basically. Is just some tiny change in x, but now we're applying it to 3 dimensions here, and this is just a 1. Okay, so this is important. We'll start with this. We can, for any expression, we can add and subtract the same thing in the expression since they cancel out. So now I can say delta f is equal to f of x plus change in x, comma, y plus change in y, minus f of x plus change in x, comma, y, plus f of x plus delta x, comma, y, minus f of x, y, right? This is the same thing. We can do the same thing. We've just added two little things here that cancel out, but now we can manipulate our expression. So if we just take a look at this, I'll put these into brackets because this is what we're going to be taking a look at. Okay, this actually looks very, very, very similar to our partial derivative, except instead of our partial derivative, right, we now have, we don't have that denominator of change in x. This is a partial derivative with respect to x. We don't have that denominator that has change in x. Here, if we take a look at this x plus change in x plus delta x is just another x value. It doesn't matter. We don't know how much of an x value, how little of an x value. But you see here it stays constant. Our x value stays constant. So let's say that delta x would be 1. And let's say that x is 3. Let's say, for example. Now we basically f of x plus delta x, or x plus delta x is just 4. That's just what it is. And so now we basically we're saying f of 4 comma y plus delta y minus f of 4 comma y. If we take a look at this, this is like our partial derivative with respect to y time, like with missing the delta y. And so these two terms are very, very similar. And so if we were to say, we can actually write this, right? So this, we can take a look at this and say del f del x is equal to, actually, hold on. And so this right here, this expression is equal to del f del x times change in y, right? We have our change in y. And so basically our derivative, if we write out our formal definition of the derivative times change in y, we just get the top part, which is this. And this part here is the same thing, del f del x times change in x. Because if we write out our formal definition of the derivative, which I explained earlier, and we multiply it by delta x, which is the denominator, the two cancel out, and we're just left with this expression here. And so now what we've essentially done is we've essentially said, and I'm going to erase the top part here. Essentially, now what we've said is that delta f is equal to del f del x delta x plus del f del y delta y. Okay, we have deltas, but where's our dx, where's our dy, where's our df? Well, if we recall, right, if we just say limit as delta t goes to 0 or whatever, or a limit as our change goes to 0 of, like, I'll say this is x, so change in y, change in x, right? We get our derivative, dy dx. So essentially now what we're going to do is if we just apply the limit to both sides and we shrink our deltas to 0, we essentially get, and I'll say limit as delta goes to 0, we essentially get df, so infinitely small change in f. This is arbitrary change in f, arbitrary change in y, x arbitrary change in y. Now we have infinitely small change in f is our partial derivative with respect to x times dx plus our partial derivative with respect to y times dy. And so this right here is called the total differential. This is called the total differential, and essentially what it's doing is it's relating our partial infinitesimals to our ordinary infinitesimals. And so this actually is used a lot in differential equations. It's used a lot in, mainly, I think its main use is in differential equations, but it's a really, really important concept to know that this kind of, this total derivative or total differential, we can relate our overall change in f to partial changes in x and y. And so if we, for example, and this is kind of one of the concepts that is required as a prerequisite one, is the parametric functions where we have like x equal x of t and y equal y of t. So if we had some function of x and y, yet x and y were both parametric functions, so we have a function of x of t, y t. That's our function. That's our parametric function. So we can actually just divide by dt, divide by dt, divide by dt, and it's the same thing. So if we want to find our derivative with respect to x, with our derivative of x of f with respect to some like parameter t, we can do the same thing with the differential, the total differential, and now we're just divided by dt. And so, and in this case, x equal x of t and y equal y of t. All right, I already wrote that, but whatever. And so this is kind of an interesting way of tying the ordinary derivative with respect to the partial derivative, because the two are very, very closely related, even though the overall, the look is different, the operations are different, they're very, very related. So this is kind of the ending point of this lecture, so I'm going to tie this up. I've basically introduced the idea of partial derivatives, tangent planes, and I've tied everything together here. And in the next lecture, I will be talking about finding the slope of a function and finding the derivative of a function, not in the y direction or in the x direction, but in any direction. And that's actually called the directional derivative, and that's my main topic of focus in the next video.